Okay, welcome everyone. My name is Sebastian Osterlund, and this is Stephan from Schaik.
Hello. Today we are going to talk about RIDL or Wogenfly data load. So you might have seen it in the news. New speculative execution bug leaks data from Intel chips, internal buffers. This is another one. This has been in the news as MDS attacks, or also sometimes specifically as RIDL and Fallout. But before I can actually start talking about what MDS attacks are, I want to give you a bit of a background. So I want to talk a bit about cache attacks first. So at the top, we have our CPU registers in the CPU. And below, we have like our main memory and disk storage. And a big problem is that the CPU registers are very fast, but there are very few of them. Whereas with main memory and disk storage, they're huge, like usually gigabytes, terabytes nowadays, but they're super slow. So one solution to overcome this is to put caches in between, so smaller pieces of memory that are faster than main memory. So this is what you see in the arrow. So the more up you go, the smaller and faster it is. The lower you go, the larger and slower it is. And a very specific terminology in cache attacks are like cache misses and cache hits. So if you miss a memory load, then it's called a cache miss. If it's in one of the caches, it's called a cache hit. And it's exactly this timing difference that we're going to use for cache attack. So what does a cache attack look like? So for this presentation, I'm going to talk about flush and reload. So you have three stages, the flush part, the victim, and reload. And an attacker usually allocates a proper way. So the first step that the attacker does is the flush step, in which case the attacker will basically flush every entry in the proper way from the cache, such as it's in main memory. And what this means is that the entries in the proper way will now be slow to access. Then the victim runs. So the victim, for instance, accesses a table using the secret as an index. And for instance, it's the third entry here that contains a secret. Now, what can the attacker do? The attacker can do a reload attack now. And he can just access every entry. First entry is from DRAM, so it's slow. Second entry from DRAM, so it's slow. Third entry is from the cache, so he knows which entry was used by the victim. So back in 2018, you might have seen Meltdown and Spectre, and after that, Foreshadow. So these are previous attacks, and for this part, I'm going to talk a bit about Meltdown because it's more related to RIDL. So what does a Meltdown attack look like? So it's very similar to a flush reload attack. So basically, you allocate a proper way, and what changes is basically the part before reloading. So what happens now is that we have a victim, in our case the kernel, that leaks accesses some kernel address. And what happens is that this kernel data is now in the level 1D cache when it does that. So now we do the flush part again. So we flush the proper way to make sure that all the entries are slow to access. And now we do the meltdown part. And the interesting part about meltdown is that basically they access a kernel address which is now in the level 1D cache, and they do this speculatively. And then they basically use that address to access, as an index to access the proper way. So now they can leak the secret by loading an entry in the proper way. Now they do the fourth step, which is reloading. So they access every entry. First one is slow, second one is slow, third one is fast. And what this means is that the byte that they actually leak from the kernel address is byte 0x3, for instance. So how did they mitigate this? There are different mitigations. So a few of the proposed mitigations are array index masking and XOR masking for Spectre and Foreshadow. We don't really care about those for this presentation. We care more about kernel page table isolation. So what does that look like? So before Meltdown, we just had one process space. So we had the user space program and the kernel in the same memory address space layout. And the problem is with Meltdown, you can leak kernel data from just by accessing virtual addresses speculatively. So what's the solution? You basically introduce two address spaces, one without the kernel and one with the kernel. And basically, once you're in user mode, you basically don't have any access to the kernel addresses. So now we have a system with all the mitigations in place, which looks like this. So we have our Intel Core i7 7800X Skylake X CPU. So that's what the first line shows. We see that it's runnable for all these bugs. And if you look at the mitigations, all the mitigations are actually going to be in place. And of course, there's also sysdevices system CPU vulnerabilities, which also shows that all the mitigations are in place. So the question is, of course, what can we still do as an attacker to such a system? Well, here we see etc shadow. So if you normally access it as a normal user, you get permission denied. But if you access it as root, you can actually, for instance, see the first line being the hash of the password of the root account. And what we show here is a RIDL program just leaking the same hash by continuously running the passwd program. And this is just as a normal user. So this is something you shouldn't be able to do. So meet Roguefly data loader RIDL. It's a new class of speculative execution attacks that knows no boundaries. And to show that it knows no boundaries, first I'm going to talk about privilege levels, which are just a social construct. So what we show with RIDL is that we can leak between hardware threads, but can we actually leak across other security domains? Yes, we can. So we can leak from the kernel, across VMs, from the hypervisor, and from SGX enclaves. We leak across all security domains. And another question that's important here is, can we actually leak from the web browser, or in the web browser? And the answer is, again, yes, we can. So we reproduce RIDL in Mozilla Firefox, for instance, and this shows that we actually have no need for any special instructions. So we leak across security domains and in the browser. Another social construct here are memory addresses. So previous attacks, so Meltdown, Spectre, Foreshadow, they show that we can specifically and speculatively leak from addresses. Our mitigation efforts basically focus on isolating or masking these addresses because of that. And so to give you some examples, so Spectre shows that you can access out-of-bound addresses. Meltdown shows that you can leak kernel data just from virtual addresses from the kernel that are mapped in. And Foreshadow shows that you can actually leak from physical addresses. So what are our solutions to that? We master array index to limit the address range that you can access for Spectre. And for Meltdown, we simply unmap the kernel addresses. And for Foreshadow, we actually have to invalidate the physical addresses in the page table. So previous attacks, they exploit addressing. And that means that the mitigation efforts are currently focused on just isolating or masking these addresses. And RIDL, on the other hand, it does not depend on addressing at all. So what this means is that it bypasses all address-based security checks. And this is actually the reason why RIDL is hard to mitigate. So one question is, of course, what CPUs does RIDL affect? So we bought Intel and AMD CPUs from every generation since 2008. And of course, we are poor PhD students, so we send the invoices to a professor who gladly pays for a system. And this is what it looks like. So we build an IKEA rack with all the hardware that we bought, all the motherboards, a massive LAN cables connected, and we test our vulnerability on all of these CPUs. And what we found is that RIDL actually works on all mainstream Intel CPUs since 2008. So these are the CPUs we actually tested it on. Then at some point, we looked at the Intel website, and we saw that they were announcing the 9th generation of CPUs. Also known as Coffee Lake Refresh. And we found the 9900K very interesting, so because it has like in-silicon mitigations against Meltdown and Foreshadow. So this means that they now try to solve this at a hardware level at Intel rather than a software level. So we decided to actually buy the CPU, and again sent the invoices to a professor because we're poor PhD students. And we got it the day after we submitted our paper to S&P Oakland. As we academics usually do. So we tested on these, and we found that it's also vulnerable on the 9900K, as you can see at the top. And then, of course, an important question is like, okay, what about AMD? So we also tried to reproduce it on AMD, and we found that RIDL does not actually affect AMD. And AMD also made an official statement about this, that RIDL is not affected, that AMD is not affected by RIDL. And so did ARM also make a statement about this. So we tested on these three CPUs from AMD, and they were also not affected by RIDL. So RIDL inside runs great on Intel, but where are we actually leaking from? This is a part of the diagram I made. So here you can see the Intel Skylake CPU. And more specifically, if you look at the highlighted boxes, you see the caches. So previous attacks, they had it a bit easy. They just leak from these caches. And the thing with caches is that they're well documented and well understood now, so we have been studying them for more than the past decade. But the problem is that RIDL does not actually leak from these caches. So what else is there actually to leak from? So there are other internal CPU buffers. So for instance, the line-fill buffer, the store and forward buffer, and the load ports. And there's also more. So there's also, for instance, uncached memory that is partially handled by the memory controller. And what we show with RIDL is that we can actually leak from various internal CPU buffers. So RIDL is actually just a class of speculative execution attacks that is also known by Intel as microarchitectural data sampling, or MDS. So for this talk, let's focus on just one particular instance, which is the line-fill buffers. So what we first did is, here's an excerpt from the Intel manual. And we first read the manuals, and what we saw, there's like some references to these internal CPU buffers, but there's no further explanation. So where would you even start? That's why we started reading the patents instead. So we read a lot of patents. Here's an overview of all the patents that I had to print out and actually read to figure these things out. And so today I can actually tell you a bit more about these things. So the question is, of course, what are these line-fill buffers? So you might not actually have heard of them. So they're actually a central buffer, so you have the caches and the execution units, and the line-fill buffers themselves are a central buffer between these execution units and the caches to improve memory throughput. And in Intel CPUs, they have the following rules. So they allow for asynchronous memory requests, load squashing, write combining, and they also allow for uncached memory. And for this talk, I'm just going to focus a bit on the first one, so asynchronous memory requests. So if you're a CPU designer, a computer architect, you're very much interested in improving the memory throughput. So your question is, well, what should I do on a cache miss? So what happens in a naive way is you send out a memory request, and you like a load and a store, and you wait for the data to come back from the memory if it's not in the cache. And what this means is that you basically block everything else in the system. You drop all the work and do nothing else until you actually get the data. So what's the solution? The LFBs actually keep track of the memory address. So you send out the memory request, and if you see that you have a cache miss, you basically allocate an entry in the line-fill buffers. And that's where you then store the address of the memory you're waiting for. And in the meanwhile, you can do other things. So you can serve other loads and stores, and you can execute any other instructions while you're waiting for the memory, for the actual data to come to the CPU. And then at some point, this memory request will eventually complete, and you have the data. And the interesting part for RIDL is basically the allocation of an LFV entry. So what it means is that if you don't zero out the data that's in the LFB, it may actually contain data from the previous load. And this is exactly the problem that RIDL exploits. So we have a bunch of experiments in the paper. But the conclusion of these experiments is what we found is that our primary RIDL instance leaks from line-fill buffers.
Okay, thank you very much, Stephan. So now you've got a bit of background on RIDL and these underlying buffers. So let's have a more practical look at what we actually can do with these RIDL attacks. What practical attack attempts can we do? So what we know now is that we can leak in-flight data, right? Stephan told you about the line-fill buffers, and basically all data goes through the line-fill buffers. So let's just get some sensitive data in flight. So we started thinking about how can we as a normal user get sensitive data in flight on a normal Unix system. And what we came up with is that you can invoke the password utility to change your password. And this has to read the etc shadow file, which contains the password hashes of all users, and especially of the root user. So what we also can do is control the affinity, so where a process is scheduled using the task set utility. So we can let two programs be co-located, sharing the same hyperthreads, therefore sharing the same line-fill buffers. So what we want to do is repeatedly invoke the password utility and execute a RIDL attack from the shared hyperthread with that one, so that we actually can get the contents of the etc shadow. Well, it turned out in practice this is not so easy. So what you have to do is either synchronize so that you leak at the exact point when the data is in flight, or you have to do some post-processing. So First of all, synchronizing, we didn't find any way to do this synchronization because you can't change the binary as an unprivileged user. So we just have to do some post-processing. But note that we can actually repeat the measurement. We can invoke the password utility many, many times. So what we do is repeat it many times and stitch the measurements together. So we have a way of getting data in flight. Well, we can leak the stuff with RIDL, which I will explain now. So here is what our RIDL attacker program looks like. So first, like Stephan explained, you have a flush and reload. So the first flush part is simple. You evict everything from the caches so that it has to load everything from memory. Then in the actual RIDL part, we start a TSX transaction so that we can suppress a fault at a later stage. So what we do is just simply read from a null pointer. This seems really counterintuitive, but since this address translation won't work, we will the speculative execution will just use in-flight data in the continuation when it continues executing. And by the way, this also works for other addresses that are not mapped, so I'll come back to that a bit later. So what we do is we use this value that we leaked as an offset into our probe array, and then later we simply time every access to our probe array, and yeah, we see the first one is slow, second one is slow, third one is slow, the fourth one is actually fast. So we know that the leaked value here is 3. So we can leak data using this program, so our RIDL attack. So now the next point is actually filtering the data because, as you might have imagined, you get all the data that's in flight. So we liken it to like drinking from a fire hose. You just get all kinds of data spewed at you. So how can we actually filter this data? Well, in this attack, what we want to do is leak from etc shadow. And typically, the first line in the etc shadow file is of the root user. So, and it's always known that this line starts with the following characters, root and a semicolon. So let's do some pattern matching here. Just consider samples where we actually start with this measurement. So what we do is we start saying, okay, we know that we should start only leak stuff with this prefix. Then we start doing measurements. Here, for example, we get a measurement that's start of URL, but that's not consistent with our previous samples, so we discard it. Here we see, okay, the first part matches, and we have some other stuff behind that. So let's consider this next byte as a candidate byte. The next thing we leak is also something else, just discard it. And here we see, okay, the first bytes are consistent with our, what we have leaked so far, so just take the next byte after this. And so on and so on, you can build up a whole string leak, the actual contents of the etc shadow. So now we have all the things to actually launch a complete attack. So yeah, what we can do is leak the root password hash from unprivileged user on Linux. But let's extend this a bit. This is, who cares about if you can leak from a local user? You usually don't give anyone access to your computer anyway. Maybe you can do it in a library or something, but let's take it to the cloud. So in this attack, what we do is we have a victim VM in the cloud, which we make sure that our attacker VM is co-located with this victim VM so that they actually share the line fill buffer. So typically, cloud providers give you shared hybrid threads with others. So nowadays, there's some mitigation in place for this, but some cloud providers still do this. Typically, normal VMs run SSH servers, right? So you always want to access your VMs. So what we simply do is, yeah, how can we get the etc shadow in flight? So it's a simple idea. On our attacker VM, we have an SSH client, repeatedly set up connections to the victim VM, which, well, will load the etc shadow into the line fill buffers. And, well, now similar to the previous attack, the etc shadow is in flight. And we can, of course, leak it with the exact same RIDL program that we had. So we have a few more examples of attacks in our paper. So we can leak internal CPU data like page tables, breaking KSLR. We can also do an arbitrary kernel read and leak in the browser. So I'll discuss the last two ones now. So the arbitrary kernel leak. So one thing that we notice is that you can actually combine Spectre with RIDL. So you can use so-called Spectre gadgets to pull data in flight, and then we can use RIDL to leak this data. So what we can do is train the branch predictor to allow an arbitrary out-of-bounds read. And yeah, so for example, in the copy from user, it's possible to do something like this. And this was work done by Georgie at Microsoft Research roughly a year ago. So what he did is found out, okay, you can call setRlimit with an arbitrary pointer, so you can train the branch predictor. So first we train it to, with a valid user pointer so that it actually goes the expected path. And then at some point we give it a wrong pointer, so a kernel pointer, and then we leak the contents of that data. So let's look at the code for this attack. So first, you have the attacker starts training it with calling setRlimit with a valid user pointer. It calls setRlimit, goes to copy from user. It will take this branch and copy it from user. It's fine. Then repeat this a few times to train a branch predictor, and at some point, you give it an invalid address. In speculative execution now, this will the CPU will speculate on the value and just misspeculate at this branch, actually pulling this data into the line fill buffer. This will actually be retired at some later point, but the data will definitely be in flight. So what you can do is use a RIDL attack and leak this data. So we have an arbitrary kernel read, and we had an attack on the cloud. So for these attacks, you still need a local account on the targets. So let's go one step further to the web browser. So first of all, in these kinds of constrained environments like web browsers, you don't have access to fancy features like TSX, and you don't have access to flush instructions that we need for our flush and reload attack. So, well, for CL flush, it's kind of easy. You replace it with an evict plus reload. I won't go into detail for this. Now you can read more about it. But basically, you can do the same thing as flush and reload without needing the CL flush instruction. Well, we also don't have transactions to suppress the warning when you dereference the null pointer, but as I already said, you can use a page, like an address that's not mapped in at this moment. And what we can do is use demand paging, which is an operating system feature where pages are actually mapped in when you access them for the first time. So then the code for the RIDL attack will look something like this. So first you evict the caches, the buffer, and then you have a new page, so called new page, which is demand pages, so it's not mapped in at the address. You haven't accessed it yet. And then you do exactly the same thing as for the other attack. So the difference is that we don't have TSX here, but we use demand paging. Well, that code snippet was fairly simple, and what we found out is that we can generate something similar from WebAssembly. And I was going to show you a live demo of this, but I couldn't connect my computer here, so we made some animations that we have in the slide. Wait. Okay, there's something wrong with the demo. Well, last minute things, of course. So let's have a look at the mitigations that have been proposed for RIDL. Sorry about the demo, too bad. Well, so Intel proposed a few mitigations. So the same thread version of RIDL where you basically don't have hyperthreading is relatively easy to mitigate. So Intel added this feature to the verv instruction to actually flush the affected buffers. If you don't have the newest microcode update, you can use a number of special assembly snippets to achieve the same thing. So, for example, this you can use this if your hypervisor host hasn't been updated to actually have the new microcode that does the modified verv instruction. For cross-thread, so for the hyperthreading instance of RIDL, it's a bit more complex because the thing is, like, if you have two hyperthreads doing things at the same time, you have to synchronize them somehow because you can just leak anything that's in flight. And So they came up with something like this. As you can see, this is a very complex state diagram of how you should schedule hyperthreads. And basically what it boils down to is that hyperthreads should never be in different security domains. So this should always be in the same security domain. So if you have one hyperthread in the kernel, the other one should also be in the kernel. And it has to wait to leave the kernel until the other one is going to leave the kernel. So this looks fairly complex, and of course the overhead might be really high. So as far as I know, this hasn't been completely implemented yet. So I've seen some Linux kernel patches for this, but it's a lot of effort to change the scheduling policy. So at the moment, we just recommend disable hyperthreading because these things haven't been deployed yet. Well, while reading the patents, Stephan made this nice diagram of the whole Schaik microarchitecture. And one thing I wanted to point out is that, okay, we and other researchers found a number of these buffers that you can leak from. But looking at how complex this is, who knows how many of these other things you can utilize to actually leak data. So what we see here is basically another spot mitigation. It's not a fundamental fix. And our point here is that these things need to be fixed because at some point attackers will start using these attacks in the wild. So we have not observed anyone using like Spectre or Meltdown for malicious intent until now, but who knows? The code is readily available for these things, so an attacker can just take them and create an exploit. So, to talk a bit about the disclosure process. So this is from our viewpoint, from the information we got from Intel. So this started then in September. Our group, we discovered the line fill buffer instance of MDS or RIDL and reported to Intel the next day. Well, of course, we're academics, so we started writing a paper and submitted it as fast as possible to not get scooped by anyone else. On December 2nd, Intel told us that there's 3 other finders that also found similar vulnerabilities or the same vulnerabilities. The names are here, Georgi, Dan, and Vladimir. So we contacted them, asked them if they wanted to collaborate on the paper, and Georgie was the only one that actually wanted to collaborate on the paper. Well, then we go further a few months in the disclosure procedure. So we had agreed to disclosure date of May 14th. 4 days before the disclosure date, Intel contacted us and said, oh, by the way, there's a bunch of other people who also found related issues. And there's a bunch of people also working on other papers, and it became a bit of a chaos. So here's a word cloud of all kinds of names of people that have been involved or found similar issues. So we want to try to credit everyone. So we create this website. So if you are one of these people who has found this, please come up to us and talk. If you haven't credited you, we'll try to add you to the timeline and everything to make the point straight that who found everything. Besides this, well, we created this website with a lot of info about this. This is really hyped at the moment, right, to create websites for these vulnerabilities. But Stephan wrote a nice tool that users can use to verify their system for all of these speculative execution attacks. So, for example, you can check if your system is vulnerable to Meltdown or Foreshadow, or also for RIDL. So it's available on the website, so download it and check your computer. You can get a lot of information out of this. So, with that, I'd like to conclude. We thought Spectre Meltdown were just one instance of these attacks, and we thought, okay, maybe we have fixed this, but turned out not to be true. We've discussed a new class of speculative execution attacks called RIDL that can leak from many of these internal buffers besides just the caches that previous attacks did. And since our attacks do not rely on addressing, it's really hard to come up with mitigations that are easy to deploy. So it needs more fundamental fixes, preferably just hardware fixes, but of course it takes a few years to deploy new hardware. What we can do is leak across basically all security domains, and we can even leak from the browser. So a malicious attacker can inject a piece of JavaScript in an ad or WebAssembly and try to steal your data. Yeah, you can follow us on Twitter, Stephan or me, or the FUSEC, so our group, and have a look at mdsattacks.com for more information. Thank you very much.